Hi, everyone. We hope that you're having a wonderful time at WiDS Charlottesville this afternoon. I'm so excited to be introducing our research lightning talks. My name is Alyssa Brown. I'm a WiDS ambassador and the marketing and communications coordinator for the School of Data Science. Today we're featuring 4 incredible women who are here from the UVA School of Data Science as well as the UVA Department of Computer Science. Our research lightning talks provide an opportunity to showcase young scholars and their research, each exploring a diverse range of cutting-edge topics and research methodologies. Each speaker will deliver a 7-minute talk that examines their current research and project of interest, followed by a few minutes of Q&A. Presenting today are Ph.D. in data science student Zoe Gray and Kaylee O'Hara, Ph.D. in computer science student Elizabeth Palmieri, and Jade Preston, who last month successfully defended her dissertation and will be graduating this spring with her Ph.D. in data science. Thank you so much for attending the lightning talks today, and we can't wait to get started.
Okay, hi. So today I'm really excited to talk to you guys about my recent work on reduced order modeling of energetic materials using physics-informed deep learning. So that's a lot of words, but we'll get through it all together, hopefully by the end of this. So first, what are energetic materials? So energetic materials are materials which store energy which can be released very rapidly when an external force or chemical reaction occurs. These materials are used for pyrotechnics, explosives, and propellants. And one of the main factors which determines how the reaction plays out is actually the microstructure. So here we have pictured on the left an energetic material microstructure where the material is actually pictured in gray, and then we have things called pores, which are air pockets in between the pieces of material. Now these pores can have various geometries depending on how the material is manufactured. So on the right-hand side, we've zoomed in to several of these pores, and you can see that the different geometry results in a very different temperature evolution. So we want to know how to model the resultant temperature and pressure evolutions based off of certain microstructures. As a material science problem, this is because we want to quickly test different microstructures and materials to improve the precision and safety of energetic materials. You can imagine that these are explosive materials, things used in propellants. You want to make sure that they're predictable and as safe as possible for storage purposes as well. And then as a physics modeling problem, its high complexity and difficulty make it ideal for a deep learning solution. So this is demonstrated from the pictures on the right-hand side. So the video at the top is an example of a simple fluid flow simulation. This simulation is not too difficult to simulate directly using the equations that we have from physics, and it doesn't take too much time or compute power either. However, below we have an energetic material simulation. If you can notice, well, the microstructure, there it is. It's highly detailed, and there's also fast transients and high sharp gradients that make it take a really long time to simulate these directly. So the data for energetic material simulation is highly computationally expensive and can take up to a week per sample to simulate. So we propose to use deep learning to learn from the few samples that we have, and then we are able to make predictions within a matter of seconds for an unseen microstructure. So in our previous work, physics-aware recurrent convolutional neural networks, or PARC, we used physics knowledge and imbued it into the deep learning architecture to make it able to learn from the few data samples that we have. And here we have achieved highly accurate predictions on unseen microstructures which can make these predictions in about 40 seconds to a minute usually, which is much faster than the previous week it takes for a direct numerical simulation. However, this model is very heavy since it has to model highly nonlinear and complex patterns, and it takes some of our highest performing GPUs to actually run. So we want to be able to do the same thing, but with an even lighter model. So we propose something called LatentPARC. Here, LatentPARC, the idea behind it is based off of this kind of graph here, which I'll explain in just a second. So imagine that we have our full-on space of all possible pixel combinations that make up an image, or in our case, the temperature, pressure, and microstructure fields. This is a very large space, as you can imagine. It's 256 by 128, usually the size that we use, times like a whole bunch of other things, so it's huge. And we want to navigate this space, and this is where PARC works, is on the green manifold there. And that lies in the original space. However, if we can somehow find a way to project this information without loss of key information and how the dynamics work into, say, a space like the orange space in a reduced dimension, we can then navigate this in a much more efficient manner while also saving on compute power and how long it takes to actually make these calculations. So we propose LatentPARC, the prototype architecture. This is a very simple prototype that was just our starting point here. And it relies on a vanilla autoencoder, which takes in the data, encodes it into a reduced dimension latent space, and then a version of PARC acts on it in that latent space, and then it can then be decoded into the original state space where we can understand what's going on with our eyes, because the latent space looks quite different. And so here are some of our current results. The current LatentPARC prototype that we have, the latent space is 1/3 the size of the original dimension of the data, as well as the model has 1/16 the number of parameters of the original model. So it's a great decrease in the number of parameters, and as such, it takes much less time to train, and as well as much less time to make predictions. So this is a great step towards our overall goal. However, you might notice that it looks pretty good. However, this is kind of cheating compared to before. Here, we are just making predictions based off of each ground truth step. So every time you see a prediction down here, it has been fed the ground truth. In the end, what our end goal is that we want to be able to predict based just off of the initial conditions, so just the first shown microstructure. So here it has a little extra help. It's still blurry, but you can see the dynamics are propagating correctly. So there's still a lot of work to be done. However, this is where things get really exciting. So this is where I'm really interested in, for my personal research, is the intersection between deep learning, math, and physics topics. So I'm currently diving into previous work that has been done in these areas, where physics knowledge is imbued into deep learning architectures, and then with a little bit of knowledge from math such as geometry or topology, as well as optimization and how partial differential equations work, we can try to optimize these architectures to make them more efficient and take up less compute power. So thank you for listening to my talk, and if you have any questions. Yeah. So, and this is just a picture from a different project. I thought it was kind of pretty, so. Yeah, Jade.
Hello?
Mm-hmm.
A couple slides back, you were showing us where you were, I think, doing dimension reduction. Did you do like principal component analysis or something, or is it just the autoencoder?
Yeah, so for right now, it's just the autoencoder, although we're exploring different methods. Currently, the autoencoder is our best bet because it's the most highly nonlinear, and it's compatible with our deep learning structure that we use in the latent space, but definitely an area for research. So.
Yeah, cool. Thanks.
I was wondering if you could talk a little bit about how you went about evaluating the performance of this. I assume with the autoencoder you'd be using like reconstruction error, but if kind of like walk through a little bit of that.
Yeah, so far we haven't done too much in depth since right now the quality you can tell with your eye. Once things get better, some metrics that we use are hotspot area as well as some other computer vision techniques that are kind of standard in the field. So, yeah.
You're saying like you're interested in implementing some like mathematical models into this. Like, do you have any rough idea what would be? And also, how do you, in what sense you think it will increase increase the performance?
Mm-hmm. Yeah. So, for example, there are certain models where you can take. So right now we're learning about, I'm learning about differential geometry as well as manifold learning. So if you can understand the qualities of your data manifold, there are potentially certain choices you can make in the architecture that support those qualities, and then hopefully can increase the efficiency of your model. So at least in terms of like physics awareness, you can, like for originally our PARC version 2, you actually can imbue the equations, the governing equations for advection and diffusion, and then have that kind of act as a crutch for your model to help it learn more efficiently.
So is it more about like feature, that step, or it's more about the modeling step, I guess?
Sorry, what, can you repeat that question?
Make the efficiency is more about like reducing feature, or it's more about like the modeling, or like.
Oh yeah, so I mean, a little bit of both. Ideally, originally, since our model already works in the original space, we would like to see if it can work on the reduced feature version. However, if this is just a prototype, if we can come up with something that naturally plays on the physics of it, and we can get a reduction that way, then that would also be good. But yeah.
Thank you.
Yep.
Thanks. I'm curious as to what other, besides the auto methods for dimensionality reduction with highly nonlinear data that you considered, and why?
Mm-hmm. Yeah, of course. So honestly, so far we've really just considered the autoencoder. There are other things such as like PCA that are more commonly known that are linear. But yeah, so far, to be honest, we've just done the autoencoder. So yeah. Okay. Thank you.
All right, hi, I'm Kaylee, and today I'm going to be talking about some research that I've done with a group comprised of individuals from UVA and UC Irvine that leverages data science techniques to analyze cardiopulmonary exercise testing data. So first I'll explain what cardiopulmonary exercise testing actually is, which is also widely commonly referred to as simply CPET. So a CPET can occur on a treadmill or a cycloergometer as seen in the upper left and bottom right pictures on the slide respectively. So when this test is being conducted, participants will wear a mask that will analyze some information of your breath. So how much carbon dioxide and oxygen is comprised in your breath, the frequency that you're breathing, the volume of your breath, and also bands are worn across the waist to collect information on your heart rate. And this test in total tends to take approximately 10 minutes, so participants are encouraged to exercise as long as they can. And the reason why this test tends to only take about 10 minutes is because the exercise is becoming progressively harder. So on the treadmill, at a gradual pace, the incline will increase, the speed will increase, and on a cycloergometer, the resistance will increase. So some work that the group I'm working with has completed is primarily regarding pediatric CPET data sets. So participants tend to be between ages 7 and 18. And the main focus is the entropy of these metrics that I discussed that are collected through the mask and the heart rate around the waist. And primarily they want to see, are there any significant differences in entropy between males and females and between maturational status in the children. So for clarification, I'll explain what entropy is. So entropy tells us how uncertain we are, it explains the uncertainty in the data. So if data is more predictable, then there is less entropy. So for example, a system with low entropy would be sunrise time. We can all look on our phone and see to the minute what time the sun will rise and set depending on what city or neighborhood that we're in. So there's low uncertainty in when the sun will rise, therefore low entropy. In contrast, a system with high entropy would be a coin flip. If you were to flip a coin, you wouldn't know for certain if it would be on heads or tails prior to looking at it, so therefore there's high entropy. And then a more extreme example of higher entropy is accurately predicting next month's temperature precisely. So we couldn't know for certain today what the temperature will be on April 28th in Charlottesville 2025. So these plots showcase some of the results that the group has previously published. So I'll try to break it down for you. On the left-hand side are the sample entropy for the males, and on the right-hand side is a plot of the sample entropy for the females. And in the light gray is participants that were in early puberty during the time that the test was administered, and in the black are the late puberty participants. And each column represents one of those different CPET metrics that I was explaining that are collected during the test. So overall, we see that participants in early puberty tend to have higher entropy or less predictability in their CPET metrics during the test than their late puberty counterparts. And also there is a slight increase in entropy for female participants than male participants. As you can see, the vertical y-axis for the females goes up to 2, while the males only goes up to 1.8. And the reason, one theorized reason for why early pubertal participants have higher entropy is that as children approach adulthood, you're fine-tuning your physiology. Another study that we've conducted is paying attention to the ventilatory threshold. So the ventilatory threshold is the point where the slope between the carbon dioxide and the oxygen in your breath begins to change. So it also can be referred to as the anaerobic threshold, so that's why in this plot the AT is pointing at that break point. So if you look at the white boxes, the white data points, you can see that it's increasing at an approximately steady rate linearly, and then eventually it switches to a more increased slope. So this is the point of interest called the ventilatory threshold, and the group has looked at the entropy pre this threshold and post this threshold to see if there's any difference in the entropy around this point. And this point is very significant to medical professionals and athletic trainers because it represents a change in your metabolic response that can be used to make better decisions about your health or your exercise training, etc. So here are the results for the pre and post ventilatory threshold on that. This is only for heart rate, and on the top is for the males and the bottom is for the females. So we see a very noticeable change, decrease in entropy post the ventilatory threshold than before. So your response to exercise is becoming more predictable in these children as the exercise progresses. With this same study, we did see a slightly higher entropy in females than in males, and there was a more noticeable decrease for the early pubertal participant, although subtle, than the late pubertal counterparts. So the work that I'm currently working on is trying to see if we can confirm these results on a new CPET data set. And this new CPET data set is also pediatric participants 7 to 18. However, the CPET administered was a different type. Now, the generalizations that I previously made about CPET at the beginning of the test still hold true, but there are just some nuances to how the test was conducted. So seeing if the findings regarding the entropy in these children are more universal versus just specific to one type of CPET. Another difference with this data set is we don't have a maturational status indicator, so we have to delineate based on the age, and we just have to acknowledge this assumption that not everyone matures at the same age, and age isn't equivalent to maturational status, but we're just going to go forward with the data that we have. So when I was attempting to calculate the ventilatory threshold on this new data set, I was not getting the results that I expected. Domain experts are fairly certain that the ventilatory threshold should occur approximately 50% of the way through the test. And I was getting, more than half of the time, getting results that would happen at the very beginning, near the very end. And so I looked into it a bit more, and a lot of people agree that the ventilatory threshold is notoriously difficult to automate. And so a lot of times what's done is that experts will manually go through and label where they're seeing that breakpoint. And especially in pediatric studies, it's not as clearly defined as in that visual there. So there is a lot of subjectiveness when determining this ventilatory threshold point. So what sometimes is a mitigator for that is to take different approaches to calculate the ventilatory threshold and average them together to account for any inherent bias that's in one method. However, when I was doing that, I noticed that sometimes these two methods were not agreeing. One could occur 20% of the way through the test, one 80% of the way through the test. So if we're averaging those together, we're really just adding in new information that's not present in either one of the methods to determine the ventilatory threshold. So what we decided to do for this study is to just look at pre and post the midpoint, since we couldn't trust the results that we were getting by automating the ventilatory threshold calculation. And we decided to look at the entropy at the first half of the test, and then compare to the entropy in the second half of the test, and then table this automation for a separate project. So here are our current results on the new data set, and largely they do coincide with the previous findings. So again, this is just showing the heart rate, which is one of the 5 metrics that we have been analyzing. Males on the left, females on the right, and we do see a noticeable change pre or post the midpoint, similar to how we saw a change pre or post the ventilatory threshold. And all in all, there is also slightly higher entropy in females, so it's not universal across every single metric. So we'll have to work with our physicians on our team to help explain why these results may sometimes be inconsistent, and also acknowledge that we have a sample size of 60, and that could account for some of the inconsistencies as well. And largely, we also see that the younger participants tend to have higher sample entropy than the older participants, just like the early pubertal participants had higher entropy than the late puberty participants. So the next steps are to really focus on seeing if we can research or create a new way to automate the detection of the ventilatory threshold, since it is a significant point in the exercise test for physicians. However, we've proved that the current methods have some opportunities for improvement, and also curious to see how outliers in the CPET data could be influencing our results, since largely in CPET studies, the outliers are not handled or regarded at all. So seeing, is there a reason that we should be, or are these outliers more few and far between given how much data we have that they don't have as much of an effect? And also, since we were delineating based on age, so for males, we made the cutoff at 13, so we had a group younger than 13 for males, 13 or older for the older male group, and then for females, younger than 12 or 12 or older than females, since females tend to mature at an earlier age than males do. However, if we were to adjust this age group cutoff slightly by females are at 11 now instead of 12, how much is that going to actually change the results that we're reporting on? And yes, thank you very much for your time. Let me know if you have any questions.
Thank you for your presentation. I would like to ask you, how did you come up with this idea and theme for your PhD, and why UVA to work on this?
Sure. So this project, I was fortunate to have connections with professors that were working on this project, and I came into this project last summer and sort of am picking up where a previous PhD student that graduated took off. And I chose UVA for the PhD program because I did the master's program here last year with the intention of sort of getting my feet wet in graduate school and seeing if I would want to stay in school for a long time. And I had a very pleasant experience in the master's program. I thought that the School of Data Science did a really good job of making sure there was a sense of community and making sure that you had opportunities to connect with professors and find a good research experience for you versus other programs that I may have looked at. It seemed a little bit more like there's more of a barrier between the students and the professors that I didn't see here.
I'm intrigued by the concept of entropy to express uncertainty. That's not something I've run into before. And I'm curious if that is a common aspect of medical research or it's something that you've developed. Thanks.
Yeah, I think it's a fairly common, it's definitely a fairly common metric in statistics to look at, and in medical research, particularly with, in this realm, there's a lot of studies on sample entropy with heart rate, but not necessarily all this breath-by-breath data with the CPET. And so most of these results that I reported on either are unpublished now or were just published last year. So it is relatively new in terms of, okay, we found these findings that we're seeing these trends. What does this actually mean for the health of an individual, or their exercise ability is still up for discussion.
Kaylee, I'd like to commend you on the fact that, one, you're a first-year student, and I definitely felt like I learned something from this presentation. I think that being a PhD student, it's about learning how to teach, and I learned what entropy meant just from your presentation. I thought it was a very good description of entropy. I've heard people say it numerous times, but I've never understand or grasped specifically what entropy meant until this particular presentation. So I think that was a very job well done. Do you think that this is going to be something you're going to focus your dissertation on, or is this just part of a lab that you're part of? I think this is just kind of a follow-on question to what you were asking.
Oh, yes, I definitely am enjoying this project, and also as my background's in industrial engineering from undergrad, so I've definitely just been more focused on more statistical computer science technical methods, and don't have prior to the PhD program, a domain that I've been most interested in applying data science skill sets to. So it took me a while to get into a groove with learning all this literature with the medical terms, the kinesiology terms, so on and so forth. And now I finally feel like with these next steps, like discovering, oh, there's a hole here with the ventilatory threshold detection, and then trying to leverage data science techniques to find that. Like as I'm learning more and going further through it, I'm getting more excited about it, and yes, definitely interested in continuing it. Thank you.
Hi everyone, my name is Elizabeth Palmieri, and I'm going to be presenting on a project that I just recently finished titled Improving Aspect-Based Summarization via Contrastive Learning with Anchored Negative Examples. So just to give a little bit of background, I have a document here. We don't have to read anything or understand anything. I just want everyone to observe. So we can see right off the bat, this is just the first page of Thomas Jefferson's biography, and it can be a little bit overwhelming because we're seeing tons of names, dates, events, a swath of information, and a user might find it to be difficult to understand what this is trying to convey. So this is the task of text summarization, which I'm sure everyone is familiar with. We have an input document, we give this to a model, and ideally we get something concise and informative, like Thomas Jefferson was the 3rd president of the United States. But thinking back to that document, we can see a multitude of facets from which we could have approached it. So there were tons of events going on in his life, different things that he did. So maybe a user isn't necessarily interested in his presidency, but more so interested in a different facet, such as maybe his involvement at UVA. So this is the task of aspect-based text summarization. So we have an input document, and we have the addition of an aspect, which is an oracle, which is guiding the model, showing the model what we're really interested in with the summary. So with this, ideally, maybe we would get something from the model like Thomas Jefferson founded UVA in 1819. So what we want is a summary that pertains only to the aspect without any extraneous information or unrelated information. So this task is quite difficult for a model to perform. So even just thinking about plain text summarization, we have different varying input document lengths, and we have the difficulty of the model being able to ascertain what's important, what it needs to take from this input document, and create an abstractive summarization. And then we create this added difficulty of of limiting the model of what information it can have and being able to draw correlations between the related information in the input document and the aspect. So in order to have the model be able to successfully complete this task, we needed to contrive some sort of methodology to help the model be able to draw correlations between related information and then create space between unrelated information. And so we leveraged this through contrastive learning, and I'm going to give a toy example right here. So an example data point we have is our aspect is UVA, and our summary is Thomas Jefferson founded UVA in 1819. So within our project, we had two different flavors of contrastive learning. We have aspect anchored, which is an example here. So if we take a look at these two data points at the bottom, we see that our aspect is the same, which is the anchor within the data set. So our aspects are both UVA. And we can see on the left, our summary reads, Thomas Jefferson was the principal designer of UVA's building and curriculum. So we can see that this is completely related to the aspect, and this would be a good example of an aspect-based text summary. But if we take a look at the right, we can see that our summary reads, Thomas Jefferson was the third president of the United States. So we can see a disconnect here between the aspect and the summary, and ideally what we want to do through contrastive learning is tell the model that this data point on the right is what we're not looking for and create space between that. And here's an example of summary anchor, the different flavor within our project. So we can see on the left, our data point is the same, and we notice at the bottom the summaries are the same. Thomas Jefferson was the principal designer of UVA's building and curriculum. But we can take a note that the aspects are different. So if we look at the right, the aspect is the presidency, which is completely unrelated to the summary. Again, telling the model to punish the model for creating a summary like this that's not related to the aspect. So from here, we contrive a contrastive loss. So basically what we're doing is we're creating a contrastive loss for the aspect anchored and summary anchored. And what it is the negative log likelihood of the probabilities of the gold standard summary S, given the document D and the aspect A. And from this, we subtract the log probabilities of a negative summary denoted by S with a negative sign, given the document and aspect, and we multiply this by lambda, which just weights the strength of the negative example. And very similar on the bottom, it's the same idea on the left-hand side of the equation of the log probability of the gold standard summary, given the document and aspect. And from that, we subtract the log probabilities of the gold standard summary, given the document and a negative aspect. So just some information about the methodology that we used. We needed to leverage some data sets in order to create these negative examples. So there are two aspect-based text summarization data sets that we use to leverage and then create these negative examples in order to fine-tune the model. So the first of which being is called any aspect. This is a news domain. I think this had over 300,000 aspects, so we took the top 10 aspects in order to reduce potential noise. And from this, we were able to contrive about 50,000 contrastive examples for the aspect-anchored and summary-anchored contrastive data sets to fine-tune our model. And a similar idea for COVID-ET, that's a sentiment analysis task from Reddit posts. And from this, we were able to contrive about 8,000 contrastive examples for our aspect-based and summary-based data sets. And the evaluation metrics that we used were Roche and Blue scores. These are traditional within text summarization, and these analyze the n-gram overlap of the gold standard summary and the generated summary. And then we also utilized something a little bit new called GPT-4 critique. So what we did is we took these generated summaries, we showed this to GPT-4 and asked GPT-4 to critique it based on metrics that are not as easily reached by the traditional metrics. So things like impurity, coverage, and GPT-4 giving a general rating for the quality of the summary. So this first table is our results on the any aspect data sets, and we can take a look at the different models. So we use some baseline models, BART and FLAN T5, which traditionally perform very well on text summarization. And then we analyzed 3 large language models, Pythia, Gemma, Llama 2, and we analyzed them based on 3 different facets. In a zero-shot setting, a supervised fine-tuning on the original data sets, and then a contrastive fine-tuning, which is our method, which is the contrastive loss, based on the 2 leveraged augmented data sets, and denoted by summary-anchored or aspect-anchored data sets. And then taking a look at our results, we can see at the bottom that Llama 2 outperformed all of the other methods, and this is our contrastive fine-tuning method. And looking at the GPT-4 results, we can see it's a little bit more randomized, which we attest to having a high temperature at the time of generation. And this graph is the results for our other data set, COVID-ET. And we can see the same trend in results where our contrastive fine-tuning method outperformed all of the other fine-tuning methods in the zero shot and the baselines with that same randomness from the GPT-4 critique. So in conclusion, this project is the first systemic analysis of LLM performance on aspect-based text summarization utilizing a contrastive loss, and our method sees an improvement in Blue and Roche scores. So that's all that I have to share. I'm happy to take any questions.
Could you talk more about the fine-tuning and how that worked?
Yeah, so let me go back. Yeah, so we utilized this loss. So we augmented the data sets and then created from these already existing aspect-based text summarization data sets. We created these negative examples that I had discussed earlier. So creating these kind of noisy data examples. And from here with the model, we're training the model and using the loss of the accurate summary combined with the aspect, and then subtracting from that the loss of the noisy example. And yeah, so we fine-tuned 3 different models on the augmented data sets and got our results from that.
Is this equation like a Kolbeck-Leibler divergence approach?
I'm actually not even sure what that is.
Okay,
so.
I just saw in one of my statistics classes, it looks very similar, so I just assumed that it was Kolbeck-Leibler divergence.
Oh, this is the cross-entropy loss, so
okay,
it's like,
then it's Kolbeck.
Okay, yeah. So yeah, that's a very common loss. This is the standard loss used within large language models.
I was wondering, my understanding is like you use something like a BERT score and then also an LLM evaluation to do the, yes.
Yeah.
Was there any human annotation, like to see how accurate both of those things were?
I'm sorry, did you say a human annotation?
Yeah.
We didn't use a human annotation in this project. Our main goal was, because the main use of evaluation metrics is within Blue and Roche scores, so this is a proof of concept to just see if we can just surpass the accuracy of these other models, but I think a human evaluation would have been a good addition to the project.
Sure.
Yeah, and it's very common within NLP.
Yeah, thank you.
Yeah.
We're running a little short on time, so I think we can take one more question and then we have to conclude. Sorry.
Hey, thank you for the presentation. I got a question. So for the different aspects that you picked, how close are they, or are they pretty widespread aspects?
Yeah, so it depends on the data set. So for any aspect, we took the top 10 aspects within that data set, and those were quite different from each other. So those aspects were and it's a news domain, so the aspects were different countries, different people, but within the COVID-ET data set, that was a sentiment analysis task from Reddit posts, and those aspects, the lines were a little bit more blurry. Like the task was to separate emotions such as like grief or sadness, so there was less distinction between those aspects.
Do you see difference in performance?
Yeah, definitely. So if we look at this table, these are the results for any aspect. And we can, for both of these results, Llama 2 was the highest performing model, but we see a different result based on which anchor was used for the data set. So here we can see that for Llama 2, for any aspect, the aspect anchor data set performed better. Whereas when Llama 2 was fine-tuned on the summary anchor data set, it performed better for COVID-ET, which we attest to the differences within the aspects. Like, so maybe the model was able to differentiate better within a news domain and relied on the summaries to be able to differentiate. But within COVID-ET, since there was a lot of nuance within those aspects, maybe leveraging having the aspects be different from each other helped the model learn a little bit more.
Okay, thank you.
Yeah. Thank you.
Hi, I'm Jade Preston. I'm a third-year PhD student, and as you can see, As you can see from the screen, I'm also a major in the Air Force. And so I recently defended my dissertation successfully, and so this presentation is going to show you the highlights of my work in advancing hyperspectral image classification for material identification. Oh, and I'd also like to mention that my dissertation was an application, or provided an application into mineral detection, and you'll see that in the slides, but it also will serve very well for other applications. Everything on the Earth's surface, natural and man-made, emits a unique spectral signature, and hyperspectral imaging captures these spectral signatures with the ultimate goal of material detection and identification. A spectral signature is caused by light's interaction with the chemical bonds of a material, which allows for them to be unique. And so this gives you a conceptual display of how hyperspectral imaging works. We have image pixels that have or are composed of one or a multitude of materials within them, and then they have an associated pixel spectrum that allows us to identify the materials in the image. And so this process of identifying the materials in the image and estimating their abundances is called spectral unmixing. And there's two main approaches. There's the linear mixture model and the nonlinear mixture model. With linear unmixing, we assume that the materials in the pixel are occupying adjacent and distinct regions. But with the nonlinear mixture model, we assume that the materials are interacting in a more complex or nonlinear fashion. This is a standard equation for the linear mixture model, and I'm providing you an example of where linear unmixing could be appropriate. We have two particular materials, allanite and kaolinite minerals, and you can think of this zoomed out region of the, is this the, can I don't know, yeah, I guess I don't know if this is the clicker is working, but you can see the zoomed out region. The zoomed out region is representing a mixed pixel. And so what I did was I'm providing you the spectra for the individual materials and their mixed pixel using an ASD field spectrometer. The blue spectrum is representing allanite, the orange spectrum is representing kaolinite, and the green spectrum is representing their mixed pixel. And so I then ground up allanite and kaolinite using a mortar and pestle or in my kitchen, and then measured measured their composition or their granular composition using that ASD field spectrometer, and then I mixed them vigorously to provide you the mixed pixel spectrum. The equation on the bottom is a polynomial equation, and it's commonly used in nonlinear models. However, there's a lot of them. You can use the Hapke model by Hapke et al., or a bilinear model, just to name a couple. And a common challenge with spectral unmixing is spectral variability. And what I mean by that is that identical materials as well as differing materials can appear spectrally different. And that can be caused due to particle size, surface roughness, shading in the region, atmospheric effects like fog can cause an identical material to look different than its identical material. And so this causes us to have a large library of reference material in order to correctly identify the material that is in the pixel. But that also can in turn result in an ill-posed inference problem and ultimately cause erroneous results and impractical solutions, as well as computation inefficiencies. And so this plot on the screen is showing you an example of a failed unmixing attempt using ordinary least squares regression. And so the plot is showing that we have a close model fit with our observed pixel spectrum. And so the observed pixel spectrum is the blue, which is representative or similar to the previous pixel spectrums that I showed you in the last slides. And the dashed line, the dashed black line, is representing our inferred model. And with regression, you're wanting that model to mirror, your inferred model to mirror your observed pixel spectrum in order to get the close fit. But what we're seeing also is that our entire spectral library is included in our inferred model, which is just erroneous and impractical. But it's also important to note that for understanding that we start with the observed mixed pixel spectrum and work in reverse to identify those pure materials in the pixel. And so spectral unmixing is commonly interpreted as a regression problem. And so for my contribution to the field of unmixing, I made a thorough comparison of regression-based approaches for unmixing. I also provided an explanation of the assumptions around ordinary least squares regression as they pertain to spectral unmixing. And it was through that analysis I developed a novel approach for unmixing pixels, but that addresses a key misalignment of ordinary least squares within spectral unmixing. And then lastly, I provided a novel taxonomy discussing the physical chemical attributes of the materials that aid in their unmixing. And so this top table is showing you an example of one of the comparisons that I made using the different unmixing approaches. And then these bottom two plots are showing you that physical chemical taxonomy that I developed. Allanite is considered to be a sulfate. Kaolinite is considered to be a phyllosilicate. And I'm showing you the typical spectral patterns according to those chemical categories of those minerals. And I use that taxonomy to further identify the attributes of the particular material that aided or thwarted their successful detection. This is a list of the body of work that I've provided within the last 3 years, and one of them is not from the last 3 years. It was probably the year prior, but this is the list of papers that I have contributed thus far, and I hope that this body of work serves not only the field of hyperspectral imaging, but also the field of data science very well. So what's next for me is in about 6 weeks' time, I will be celebrating my promotion to major, and thank you. And that will be on May 15th at 4 o'clock. You are all invited if you would like to come. And about 3 days later, I will be graduating because, well, I get to graduate because I defended my dissertation, and then, thank you. And then afterwards, my husband and my dog and I, we will be PCSing. We will be moving from the Charlottesville area and onto our next Air Force adventure into the wild blue yonder. Thank you.
We have time for one question. I know we're running a bit behind. Any questions for Jade? Yeah, Erica.
Yeah, because I was seeing this and I was like, oh my gosh, like I could see like 20 years from now I'm watching true crime and they use this. So like, what are your hopes maybe for future applications of this? Like where, or just some ideas you're like, okay, maybe this is where someone will use my research to develop something or refine in any area.
Right. Thanks for the question. I would say the military answer would be like detecting bombs or IUDs out in the field so that, you know, we're protecting our airmen or protecting our soldiers out there. Another application could be for disaster relief. I know that there is some research that's been done or that was done for identifying or finding people after, I think it was the Haiti or was it an earthquake or something like that? They were finding individuals that were on their rooftops, and that was very successful. I think another thing is what is it called? Food security. I did a paper on food security and identifying the health of crops. So with hyperspectral imaging, you can identify healthy crops versus non-healthy crops, or different crops that can that provide different nutrients for different communities. And so that's another application. Yeah. I think that was the only question I'm allowed to have. So thank you.